And I'm David Williams. I'm one of the faculty here at the Institute of Particle Physics. And this is a slight variation on the title that I was given, which was ground-based gamma ray astrophysics. And it's true that what I'm going to be talking about is our measurements done from the ground, but the more interesting aspect from a scientific point of view is not where we're doing the measurements, but the energy range that we're covering. And by the very high energy gamma ray range are gamma rays above 100 GeV. So there are several methods that are used for detecting high energy gamma rays. One, I think you've had a talk already about Fermi, the Fermi satellite and gamma rays with Fermi. And so that's a whoa, what's happening to the text here? So Fermi is a satellite that covers the energy range from about 100 MeV to about 300 GeV. And when you go to higher energies than Fermi can look at, you need a larger detector than you can launch in a satellite. The gamma ray fluxes are very small, and so that's what guides us in the direction of using instruments that are on the ground. And there are two main techniques that are used. One is the atmospheric Cherenkov technique, which I'll talk about, and I'll talk about both of these. And the other is the air shower technique, for which Milagro and Hawk are examples. So what happens, how do we detect 100 GeV gamma ray from the ground? Because 100 GeV gamma ray doesn't make it through the atmosphere. It interacts high in the atmosphere, collides with one of the atoms in the air, and produces an electron and positron. And that electron and positron then, in turn, collide with the air again and radiate high-energy photons by a process called Bremsstrahlung. And those photons then, in turn, collide with the air and produce another electron-positron pair, and so forth. And so you have an exponentially growing cascade of particles in the atmosphere.
So the Bremsstrahlung is also gamma ray?
The Bremsstrahlung photons are gamma rays. So a charged particle that goes very near the nucleus of an atom, it gets deflected because of the attraction of the electric, or repulsion of the electric charges, and as it's accelerated as a result of that electrical force, it can emit a gamma ray. And so you have this exponentially growing cascade of particles, and if we want to detect the gamma ray from the ground, then we have to look at what actually reaches the ground from the shower. And one thing that reaches the ground is if the gamma ray has enough energy and the shower is big enough, some of the particles will reach the ground before losing all their energy in the atmosphere. And also, there's light that's produced in the shower by what's called the Cherenkov mechanism, and that light, optical light, the atmosphere is transparent to that, and so that optical light reaches the ground. And so to demonstrate this effect of the showers, I have some simulations that were done by graduate students that worked with me quite a few years ago now here in Santa Cruz. And so this first simulation is going to be a 2 TeV. So T is the metric prefix for tera, or 10 to the 12th. So this is a 2 times 10 to the 12th GeV gamma ray shower, and these were done when we were involved in the Milagro experiment. So this is sort of done in the context of Milagro, and the particles in the shower are going to be represented by little colored dots. It's a little bit hard to read the key here, but the blue dots are going to be electrons and gamma rays. Yellow is muons, green is pions and kaons, purple is protons and neutrons, and then red is anything else, and mostly those are nuclear fragments.
Quick question. What's the logic of putting electrons and gamma rays as the same?
The logic there is that their interactions are very similar. So these are the so-called electromagnetic particles in the shower that are interacting with the nuclei by electromagnetic force. All of these other particles are produced by strong interactions involving nuclear collisions between protons and and our cosmic rays and the nuclei. So what you'll see is, in fact, in the gamma ray shower, almost all of the particles are blue, and I'll show a proton shower in a minute, and we'll see then that there's actually a larger variety of particles in the shower. And these are available on the website here on the SCIF if you want to download these and look, and there are some additional ones besides the ones I'm going to show. So it's just going to work. So what you see is that the high energy particle came in here right at the center of this grid. So there's a purple particle, so it's something that was knocked out of a nucleus. But most of these particles, most of them in the gamma ray interaction are electrons and photons produced by these processes I described. There was a muon, one muon that you saw there, a yellow particle that used to be green. I'll run through this again. So what's happening here is, it's as if you're lying on your back looking up at the sky, and these particles are coming down towards you. There's a little counter here that's picking up the altitude, and so that the simulation stopped when it got to the altitude of the Milagro detector, which was at about 2,700 meters, or about a little over 6,000 feet in New Mexico. So I'll do this again from the beginning. So again, we start out with the one particle. Now we're up at about 1,500 or 15,000 meters or 15 kilometers initially. There's a nuclear fragment, the purple particle. There's a muon that appears here. At some point, did we miss it already? Oh, no, there it is. Oops, it wasn't there for very long. But both these particles, electromagnetic particles, and you see that most of the particles are concentrated here within the center of the shower. I think this grid is 20 meters on the side, if I remember right. The beginning, the intro to the movie said so. So this is what a gamma ray shower looks like. For comparison, this is the analogous simulation for a proton shower. So a lot of in addition to gamma rays hitting the atmosphere, there are a lot of cosmic ray protons hitting the atmosphere as well. And the interactions here are very different. They're less frequent, but when they happen, they produce a lot more particles. So the interactions that the gamma ray produces, you're always having one particle produce one particle going to two. But when a proton collides with a nucleus, you can have a single collision producing 10 or 20 particles, mostly pions. And so the pions are the green particles, the green dots. You see a lot of yellow particles. These are muons here. These would be the muons that you'd be, if you're detecting cosmic ray muons, this would be the origin of those muons in the atmosphere. They're being produced in the atmosphere by these protons, by protons and other cosmic rays colliding with the nuclei in the atmosphere, producing pions, but then subsequently decay into the muon. So if you follow some of these green particles, you'll see that they turn yellow. That basically they start out as a pion, and then the pion decays and produces a neutron. Or produces a muon. If you follow any of the green dots for a while, you'll see after some period of time, most of them will turn yellow. Either that, or they'll have another collision with the nucleus and produce another interaction. What you see when this, like there was a collision way up here that was one of the particles. So there are a number of differences you see here in the interactions with the protons and the gamma ray. The gamma ray interactions tended to produce particles that were all very close to the axis of the incoming particle. And here, the collisions you see sort of produce these explosions of particles that are being knocked off to much larger distances from the incoming particle. And so this looks very different by the time it reaches the detector than the gamma ray shower. Where the particles are spread out over a much larger area. There are several muons in the shower, and and fewer gamma rays and electrons. So this can be used to differentiate the gamma rays from the proton showers in order to reduce the background. So I mentioned that this concept of Cherenkov radiation, which is important to both of the ground-based techniques for detecting high-energy gamma rays. And you can think of Cherenkov radiation as the electromagnetic analog of a sonic boom. So when something goes through the atmosphere faster than the speed of sound, you get a shock wave, and that shock wave, that acoustic shock wave, is the sonic boom. When a charged particle goes through a medium faster than the speed of light in that medium, you get an electromagnetic shock wave, which takes the form of emitted light, of this Cherenkov radiation. And this picture looks a little bit like a boat going through water. And if a boat goes through water faster than the speed of waves on the surface of the water, you get a wave that's sort of trailing behind the boat, that's propagating in a direction perpendicular to the wave. And basically the same thing is happening with Cherenkov light. You have a charged particle going through a medium. The light is propagating out to that particle at a speed that's slower than the particle is going, and you get a wave front here and you can calculate the angle of that wave front with respect to the angle of the particle based on the velocity of the particle and the velocity of the speed of light. And so you get photons, and this wave front is basically optical photons propagating along the normal to this wave front. And so this is a mechanism that relativistic particles produce light in the atmosphere when they're moving through the atmosphere, and also if the particles when they get to the ground, if they go through a clear transparent medium such as water, you get Cherenkov light in the water. And I don't know if you've seen pictures of nuclear reactors that are underwater. Those pictures usually show there's sort of a sky blue glow around the reactor, and that glow is from the Cherenkov light that's being produced in the water by the relativistic charged particles that are coming from the reactor.
I've heard it said that some people can actually see with their eye the blue flashes in the sky from this. Very faint blue.
I think, also I think it's possible if a particle goes right through your eye, that you might be able to see a blue flash of light produced directly in your eye from the Cherenkov effect. But
your eye becomes a detector.
I've heard that as well. I haven't experienced it myself, and I think it would take a fairly large shower in the atmosphere to be able to see it. But I wouldn't rule out that it's possible. So I said that the one way to detect gamma rays is to detect the particle to reach the ground, and Milagro was an experiment that did that using a large tank of water with photomultiplier tubes in the water. So this is sort of a schematic. There was a large water tank, and there were photomultiplier tubes in 2 layers in the water. This is an actual photograph of the detector. You can see here the tubes that are near the surface, and then it's hard to see in the photo, but there are rows in between of tubes that are down at the bottom of this detector, and it's about 6.5 meters deep, the water, and the detector. This top layer, these top tubes are about 1.5 meters below the surface, and the bottom tubes are down about 6.5 meters from the surface. In this particular picture, there's a big black light-tight cover that sits on top of the surface of the water, but we had blowers that we could basically blow in and inflate this cover to work underneath it when we were doing repairs. And in this photo, the cover is inflated and it's up off the surface of the water. This back here, there's actually somebody in a small raft that's working on repairs that has a lamp with them, and that raft drifted a little bit during the time-lapse photo. So that's what this slide is. So this is one of the detectors that's been used to detect very high energy gamma rays from the ground.
Does that water have to be super pure?
The water does need to be very pure in order to have a good transmission for the Cherenkov light that's produced in it. And so it was recirculated, it's filtered. It doesn't have to be sort of the level of distilled water or deionized water. It's still, it's been filtered through carbon filters to remove any organics, and and has a UV lamp to kill anything that might be alive. And so that's, I have now simulations. So we looked at that 2 TeV gamma ray going through the atmosphere. Now I have a simulation of what happens when the particles that made it to the ground hit Milagro and interact in the water. And, oops, the color scheme is a little bit different here now. Now we have red for electrons and positrons, and green are gamma rays, secondary gamma rays that are in the shower, and now blue corresponds to the Cherenkov photons that are produced in the water. And this is looking at the size. We'll have to see the particles coming down above the pond and then hitting the surface of the pond and starting to produce Cherenkov light.
And the Cherenkov is produced entirely from the protons and electrons, positrons and electrons.
Right. You need a charged particle to produce the Cherenkov light. So the secondary gamma rays will not produce Cherenkov light directly, but if they interact in the water and produce an electron or positron, then you can get Cherenkov light from that. So here are the particles coming down. The purple line is sort of a reference point of the leading part of the shower. So this first top line represents the surface of the water. The second line represents the depth where the first layer of phototubes is, and this lower line represents the depth where the second layer of phototubes is. And I'll play this again. Again, the particles are coming down, and there's a very bright region right in the center where the concentrated particles in the shower is, and you get light produced in the water as the particles go through. So this is the same shower. Looking now, imagine that you're sort of underneath the water, looking up through the water at the particles coming down at you, and so now this purple box sort of represents how close the particles are to you, and so it's sort of, in perspective, it's expanding as you come. And the point that the purple box is the same size as this square, that's the point at which the particles are just reaching the surface of the water.
So the square is the whole size of the pond?
Well, the pond itself isn't square, but it must be approximately the size of the pond. And so because the Cherenkov light is mostly produced at an angle that's defined by the speed of light in water compared to the relativistic particles. So what you get is you get these little rings. You get Cherenkov rings. Now, if you look at for each little particle, sort of makes a little ring of light that's sort of propagating outward from the axis of the particle. And then there's this sort of big ring, which is a superposition of the light that's produced by all of the particles that are very near the center of the shower, the so-called shower core. Okay, so what we can do then is we can use the information that we get from the Cherenkov light that's produced in the water to reconstruct information about the gamma ray. So what's shown here is a representation where the position of each of these dots represents the time at which one of the phototubes in the pond recorded its signal, so the height here basically represents the time delay. And when you see it, these all basically line up in a plane. So this would be a gamma ray that was coming in, shower is coming in this direction. The tubes here were hit earlier, the tubes here were hit later. And by reconstructing those times, we can reconstruct a plane of the particles in the shower, and then the normal to that gives the direction to the shower. This is a real event. This is actually a simulated event, and it works the same way in either case. And then from the intensity of the light, we could basically determine where the center of the shower was, where the gamma ray would have hit the ground if it hadn't interacted in the atmosphere. That's referred to as the shower core. And so proton showers, as we already saw, look quite a bit different. So this is now the proton shower going into the pond, look a side view, and we have the same key as we had before, but now there are muons in the shower as well. So they're, in addition to their red for electrons and positrons and the green for secondary gammas, we have yellow for muons, and then blue is again the Cherenkov light that's produced in the water. And so here you see, for example, there's a muon right here near the center of the shower, and that muon just plows right through and keeps going. The lower energy particles, the electrons and positrons and the gamma rays, they lose their energy very quickly near the surface of the water, but the muon is very penetrating and just keeps plowing on. This just keeps going all the way through. And this is one of the...
the muon itself is creating a Cherenkov.
The muon itself is creating a Cherenkov light. So there's one muon here right in the center, and that's sort of just barreling through here and producing Cherenkov light all the way.
It's also ionizing the atoms, is it?
That's right, also ionizing the atoms at the same time. And it loses energy. It's losing energy as it does that, but it has a lot of, it's not losing energy that quickly, and so it's very penetrating. So the Milagro was shut down in 2008 after operating for nearly 10 years, and there's a successor now to Milagro, which is using a lot of the same equipment. The phototubes are being reused and the electronics are being reused. This is so-called HAWK, the High Altitude Water Cherenkov Detector. So Milagro was at an altitude of about 6,000 feet. 6,000 or 7,000 feet. The HAWK experiment is at about 14,000 feet. It's on the slope of Sierra Negra in Mexico, which is a dormant volcano, and at very high altitude. And so by being at a higher altitude, you intercept the shower before a lot of the particles have been absorbed in the atmosphere. So more of the particles reach the ground. You get more information about the shower, and you can detect gamma rays with lower energy. And this is an actual photograph of the experiment under construction. When the experiment's complete, it will actually fill this whole pad, this whole level region of ground. I think that at this point there are about something like 60 of these tanks deployed. So each of these that you see here is a large water tank. To set the scale, this is a semi-trailer here. So these are very large tanks, and in each tank there are 4 photomultiplier tubes at the bottom of the tank. The tank stands some, I think it's a border 5 meters high or so. I haven't been working directly on HAWK. I did work on Milagro, but I've not been working on HAWK, so I'm not as familiar with some of the details on HAWK. But
which school is mainly coordinating this?
So most of the same groups that worked on Milagro, including the University of Maryland, the group of Los Alamos, Michigan State, Georgia Tech, Penn State, Wisconsin, UC Irvine. In fact, there is somebody here. There are a couple people here at Santa Cruz that are working on HAWK. An engineer, Michael Schneider, and Pavlos S. Parkinson. By using these large tanks and putting a few multiplier tubes in each, the hog will cover about 10 times the area of the Milagro pond. So it has a much bigger physical area, detects more particles in the shower, and does a better job of discriminating gamma rays from cosmic ray showers from protons. And so it has that gives a much better sensitivity, of about a factor of 15 or so better sensitivity than the Milagro had once it's completely constructed.
The tops of the tanks, are they some plastic?
So there's
Window?
some sort of the tanks have a round steel frame, that inside that frame there's a plastic bladder to hold the water. And then on top of the tank, to protect the bladder from UV radiation and to have any rain that comes on the tank sort of spill off the sides, there's sort of a cap, a canvas covered cap over the top of the tank. So what you see here, these brown tops are this protective canvas cap rather than the actual. But the bladder that holds the water is black.
And then so they are light tight.
And they're light black, yes.
So the 4 photo tubes that are in there, are they arranged vertically at 2 depths?
The 4 photo tubes are all sitting on the bottom. There's a new 10-inch diameter photo tube that's positioned at the center, and then